So in this video, we're going to talk about liquids, and mostly it's kind of relationship with vapor. But liquids is just any substance that has a definite volume, but it does not have a definite shape. All right, the shape is pretty much undefined, and it's dependent on the shape of the container that it is in. All right, um, so that's a liquid. And so, like for example, if we have a closed container. All right, so this container is closed at the top. All right, so here we will have your liquid substance. Now these liquid substance, um, they have a little bit more energy than those than its solid counterpart. All right, so and that's because that the intermolecular forces that's holding these particles together are not as strong. So these molecules are moving around each other. They're able to take the shape of the container in itself. But now individual molecules, I mean, they all are in constant motion in liquid state. And so if a particular molecule or a particular particle within the liquid has enough energy, right, it will have enough energy to break away from the all the intermolecular forces that's containing in its liquid state, and it'll be able to free itself into its gaseous state. All right. When this happens, this here we call a vapor. Okay. So this is called a vapor, and it's basically gas molecules that, or molecules that are able to freeze liquid state to its gas state. All right, call it vapor. And this is something that we pretty much see like anytime it rains, right? And you have all the water on the ground, cement floor, and stuff like that. And eventually, sometimes depending on, the temperature or whatever the case is, you could kind of see steam coming off from the floor from the water, and that's just water vapor. It's water having enough energy to break away from its liquid state to its gaseous state. So water vapor. Okay, so if a liquid is in a closed container like I drawn here, all right, the random motions of the molecules occasionally brings the gas back into the liquid. So sometimes you may have gas that goes back down, and the intermolecular forces attracts that molecule, and then they will return back to its liquid state. So it's just this constant motion left and right, going up to gas form, back down to the liquid form. All right, and so when evaporation, so when liquid becomes a gas, and condensation, and where gas becomes a liquid, takes place at the same rate. And so if we're talking about the rate of evaporation, and which equals to the rate of condensation, all right, and the concentration of vapor in a container remains constant. All right. And so and then that kind of makes sense. So when, the same rate of these two are going back and forth are the same, then the vapor pressure, all right, so the vapor pressure, so we're talking about the amount of vapor within this closed container, it's constant. All right, and vapor pressure is basically the partial pressure of the vapor molecules in an equilibrium within a container. And so just to reiterate this, all right, just to kind of say it again, just in case you missed it the first time. So when we have the rate of evaporation, all right, which equals the rate of condensation, all right, so evaporation, remember, is when we're having a liquid becomes a gas, is equal to the rate where the gas becomes a liquid. All right, then we could say that the concentration or the amount of vapor, all right, so the amount of vapor is constant. All right, this means that this process here is what we call is at equilibrium. Okay, because we don't have a change over time. The change of the amount of liquid and the amount of vapor doesn't change, even though it's constantly moving, but it's doing it in a constant rate. Okay, and so when this is the case, we can measure what we call the vapor pressure. All right, and the vapor pressure is basically the partial pressure of the vapor molecules in equilibrium with the liquid itself. Okay, now vapor pressure depends on the temperature of the substance, okay, and the identity. So depending on what it is, right? The vapor pressure will tend to rise with increasing temperature. All right, and this kind of makes sense. The higher the temperature, the more, the closer, the more energy the substance will have. If they have more energy, then more likely a lot of the atoms will be able to, a lot of the molecules or particles will have enough energy to become or go to this gaseous state. All right, and then likewise. So the vapor pressure, as I said, vapor pressure, the boiling point, it all depends on the intermolecular forces that's at work between the liquid molecules. All right. So the stronger the intermolecular forces, the lower the vapor pressure. All right. Because simply means that the gases do not easily, or that the substance do not easily able to go to this gas state. All right. And the intermolecular forces, just like we stated in the previous video, the strength of it also affects the boiling point as well. All right. Now, so when the vapor pressure is equal to the atmospheric pressure, all right, it's at this point the liquid will boil. All right, and boil completely. And then lastly, the normal boiling point is the boiling point at a pressure of exactly 1 atm. All right. And so when it comes to things changing phases, all right, there is actually two things that affects the ability of something to change phase between solid, liquid, and gas. Most of us, we know for sure. It's like, well, if I want something to melt, if I want something to boil, if I want something to freeze, if I want something to condense, I have to change the temperature. All right. And that is true. But another factor that affects the state of something in its state is actually its pressure. All right. And so you could keep a substance temperature constant, but if you change the pressure, you could change what substance or what state of matter is in. Okay, and so this is why the normal boiling point comes into play, in which that if you are changing both the pressure and the temperature, and if you have the pressure to be at 1 atm, then at 1 atm, what temperature will that substance boil? All right, and with that temperature is basically what we call the normal boiling point. All right, and most things that we see here in on Earth, as long as it's around, and most of us live around 1 atmospheric pressure anyways, and so anytime we watch something boil, it's boiling at the normal boiling point. Okay, but for example, if we're in a different place where the pressure is much higher or much lower, then that boiling point will definitely change. Okay, and so, like, for example, if you were in Jupiter, all right, the boiling point of water will not be 100 degrees Celsius. All right, it'll be actually it'll be different because the pressures on Jupiter is much different. Is actually much higher. All right, and so if you were to take at the same temperature to Jupiter, where the pressure is much higher, then liquid water will actually be in its solid form. Okay, because the higher the pressure, you're squeezing those molecules closer together, and so it's going to force those molecules to be in its solid state. Okay, so just to kind of give you that illustration. Now, another measurement of liquids, or another properties of liquids that we typically study, is what we call viscosity. All right. Now, viscosity is basically the liquid's resistance to flow. All right. So what does that mean? Well, the slower it flows, the higher the viscosity. All right. And so, like, for example, if you were to take, like, maple syrup, it flows slowly, so it's very viscous, has high viscosity. Glue, glue, like Elmer's glue, stuff like that, high viscosity, it's slower. What affects the viscosity? Well, it's intermolecular forces. All right. So the stronger the intermolecular forces, the viscosity will increase. All right. And so that's basically the relationship between viscosity and intermolecular forces. And another example, or another property of liquids that's often studied, is what we call surface tension. All right. Now, surface tension is also affected by intermolecular forces. All right. In which it measures the strength of the intermolecular forces that's experienced by the molecules at the surface of the liquid. All right. So, like, for example, we're talking about, so like if we have a liquid, this is like the surface of the liquid, right? And so if we have the molecules that makes up that surface, or what we're looking at is the strengths of these intermolecular forces of the molecules of the surface. So the stronger the intermolecular force, the stronger the surface tension. Okay. Now, there are certain organisms that actually take advantage of this. Water typically has relatively a high surface tension, and this allows a lot of insects, like mosquitoes. Mosquitoes can legit sit on water. They seem like they're standing on water. Certain insects, they are able to glide on water as well. There's even a particular lizard that is able to run and walk on water, and that's simply just due to the surface tension of water, which is affected which is caused by the intermolecular forces that we find on the surface of the water. And particularly for water, is hydrogen bonding. And hydrogen bonding is relatively strong, a strong intermolecular force. All right. And so that's what the surface tensions are. And so these are some of the properties that we typically study when we're looking at liquids.